Okay, so I will do um, a so-called goudanker in Dutch. I have no idea how to translate it into English. By the way, I forgot to copy my pictures of the goudankers, the anchors, to this laptop. But imagine that you have a construction site. You take out some ground. You have some sheet piling. There's always a set of anchors to prevent the collapse of the sheet piling, that sort of stuff. And Jo showed it already on the picture. But imagine that you have some pre-stressed strands, and it's connected to a mortar block or something, and then you stress it, and you have to distribute the pre-stressing load to the sheet piling. And this let's call the anchor, and the anchor is, I did a consultancy job based on, I had to distribute it and introduce the load into the wall. So for this, I used a model based on surfaces, so sheets or plates, and solids. And why did I use solids? Because you can imagine that you cannot model the behavior of introduction of loads with only sheets. Sometimes we call it deep beams or something. You have the fact that the load also in Z direction, for instance, has considerable influence on the stresses in the model. So this is what I would like to start with the anchor block. So the idea is I have some sort of block and a set of strands. And the strands have to introduce the load to the structure that is behind it. And this is a very simple, let's say simple solid. And by doing this, I have two examples. I will show you how the solids are done in RFEM. So we start from something really simple, I hope. So start with a model. Everything is done in 3D, yeah. And I say, okay, this is 1, 2, 3, 4, 5, like that. And what we did, we prepared RFEM for the modeling in millimeters. So I used the template to get it done. And if you zoom in, you see some sort of grid. And in this grid, I will start working. And what I will do is, I will create the solid by extrusion at first. That is the most common way to create a solid you can create. And you know that RFEM has a set of, the basic points are nodes, and then you have lines, and from lines we have surfaces, and from surfaces we create solids. I will do the same. I start with directly drawing a surface and then extrude it. What I will do is draw a line, for instance, started, and here you can see the set of lines we have. I use this circle a lot in this presentation. So, circle, you know that I can change Cartesian to ortho. I will work in ortho in this way. And I will start with setting the radius, maybe it's 120 or something. Yeah, like this. So this is circle. I use this a lot in solid modeling to select surface, create surface definitions by selecting the lines. So this is a function that I will use a lot, select boundary lines. And what he will ask is, if I make a surface definition, what are the parameters of this surface? So in this case, I will create a null surface. The solid will have the stiffness, not the surface. The surface is just geometry. So it is like a line. Line doesn't have stiffness, and the surface is similar. It has no stiffness, so it's nil. So I say OK, click on it, and there is a circle. And if you are slightly experienced, you know that this coloring says it is a null surface. Now that's not so really difficult. Now I will extrude this surface into a solid. Yeah? So I create a really thick slab. That is what I want to do. So what I do is hover over the surface and then right mouse click extrude. There's the extrude commando. You can do it in some other way. I will also show you, but this is extruding into solid. If you zoom out, you see a preview of the solid that I can create. And if you look here, there's a step. I can set it here, for instance 50, like that, and then the load step is like this, and I can simply click now, and then the solid is created. So I say apply by clicking, and you see now there is now a solid, but also this solid, I didn't define any stiffness yet. So, but here you see in the navigator that I created a solid with also nil stiffness. But I can change the solid type to material, and then define, in this case, steel grade S355. Yeah. So now we have a real solid. Yeah. It is not a plate, but really, if I click on it, you see that there is no stiffness anymore, thickness of the surface. The geometry is bound by the surfaces. That's why we have the boundary surfaces 1, 2, 3, and we have only material. Yeah? Okay. Now I want to do what I want to subtract, for instance, something from it, or create a hole in the solid. Because you know the strands, the strengen in Dutch, the strands have to be in the block and anchored, and that's why we need a cavity in the solid to create it. Okay. What I do also a lot is change this. This mode is your wireframe mode, and in solid modeling you use this. You get a point for a node. This is not a real for a solid. This is not a real node, but it is just to click on the solid. And similarly, we have this for the surface. It's a dashed lines with a slight offset. Okay. What I will do now is say, okay, at some point in this surface, top surface, I have an opening. Yeah? So I go here to new node, and there's a really nice function here in solid modeling, node between 2 points. So I click on 2 points, and then on this imaginary line at the absolute or relative location, I can add a new node. So I will do this like that. And click where there's, if you zoom in, there's 1 here, and there's another node here I can click on. There's 2. Now you ask, where do you want to place the node? Let's say at 50 millimeters from the first point, there's now a node. Yeah? And this node I will use as a help node in this case. I use this a lot, help lines and help nodes. I change the origin of the work plane to this point. I do this again, that I say okay, or I can use a direct command, create opening by circle, like this. Click on here, and I click on the node, and I type, for instance, the radius. And let's assume the radius is something like 20. Yeah. Okay. Yeah. Maybe you noticed, but for RFEM has a way of detecting objects. In a surface has the way of detecting objects. If I double click on the edit surface, there's the integrated tab. Yeah, and we get sometimes support questions about it, but for planar surfaces, we automatically detect are there lines in the surface, are there nodes in the surface, and also in this case, are there openings in the surface. So already the surface detects automatically, hey, I have an opening. Yeah, that's what happened here. This opening I can use, and I'm going to extrude this line into a surface. So what I did was surface into a solid, but I can also use lines to extrude surfaces. What I will do now is click on the line, yeah, and say move, copy. I use now the copy command, make 1 copy, I say, okay, the z-axis is upwards. Let's go down to -30. And in the meantime, I use the expanded settings of copy. I want to create automatically a surface. Yeah? And the surface, it is a circle, and it will be like a pipe, a pipe surface. So I select a template for the surface. It's again a nil surface, like this. And I have to double click, and you see that there is now a surface like that. And so if I click here, you see that something has happened here. Yeah. Okay, now you see why we use wireframe, because I cannot select here. So I go back to this, or transparent mode, or this mode. And in this case, I'm going to change the diameter of a circle. We still recognize this line as a circle, so I can change the diameter quite easily. And the surface definition will change with it. Yeah. So it's like this. So I have something like this. And remember that this strand has a plug, and this plug will go inside. Yeah? And then it's fixed. That is what I want to model. Okay. So here, this surface, you can click here, and now I see this bottom has no surface yet. So I will use this. Maybe I will go slightly faster now. I will use this function, new plane load, plane surface. Okay. Click, and there it is. Yeah? Okay, if I look now, it looks like this. I use Control and the middle mouse button to nicely navigate. You see here, there's the cavity now. Yeah. Okay. Surface, the solid doesn't recognize it yet. It's not automatic. I have to define it. But first, I want to copy it several times. So I create a nice pattern. So it's something like this. I select it by. If I go from right to left, it is purple, but if I go from left to right, it is yellow, and then I can select only what is inside the box. So I say, okay, this, rotate, number of copies, 5. I can everything that is blue, I can directly type it. Type here 60 angle degrees, so I have 6 in total. I have to define the axis of the rotation. You can always look at the picture here if you unsure of what to do. So in this case, set is okay. Just click on the point here. That is some point here. I will use this origin node, yeah, like that, and I say okay. Then everything is copied, but I made a mistake. I'm still, when I do the copying, I still create automatically surfaces. That's okay. You do. This happens, and this is normal life. So I say Ctrl Z, undo. A nice thing, selection is still kept. Go back to rotate, and there's the expanded settings. So this window is similar for mirroring, copying, and rotation. I just have to unclick this here. Yeah? Okay, do it again, and it's done. Okay. Now we have the solid here, yeah, like this. What I can do is I can either throw it away. The solid is a definition, and I'm not throwing away any of the surfaces. So what I can do this and create a new one. Say go here to solid, or this button, say new solid, like this, and then it has this boundary surfaces. Just select everything like this. Everything is selected, 1 to 15. Press OK. Okay, and there's the solid now. Here, it looks like this, and he has recognized all these cavities, yeah, for the plugs. Note that sometimes your video card can give problems here in rendering. It is a solid 3D object. He doesn't have any clue sometimes how it will look. So if you sometimes when you mesh it, the solid, the shape of the solid will look better. Huh? Okay. What I will do is add some support. So I click this line and use the offset command. Yeah? Offset. Go here, because I want to add some. If you're unsure where you are, in this case, sometimes it's better to use perspective mode, and then you have slightly better understanding where the model, how to look at the model. So I use this line and say, okay, tools, set parallel line, yeah, like this. And I say, okay, It was 120, so let's go to like something like 55. Yeah, but go to inside. Yeah, like this. So this is the Y definition. If you look here carefully, there's the definition of the line. X is along the line, Z is downwards, and Y is perpendicular. So that is plus or minus. I say simply apply like this, and there is the offset. Yeah? So now I can add line support, and my model is completely supported. So I will use a rigid support like that. Click on it, and there it is done. Yeah. So my model is completely supported, and now I would like to mesh it. Go to calculate, and there is the option this generate FE mesh, for instance. And you see that we mesh it automatically, the solid. And maybe people who have also attended the seminar about nonlinearity, they know that this is not a real curved surface, but the surface is planar. But the mesh allows you to create more accurate results. Yeah? Why is this? If you look here, there is a finite element like this. I will try to explain that. Yeah, the solid is 50, and we need about 4, 5 finite elements to model effectively the depth of the solid. So, and you notice already that there is something like FE mesh settings, and by default we set it maybe 500 or 50, but in this case I would like to change it to 10. Yeah. Walter will explain a lot more, maybe about meshing, something more. Yeah. So generate FE mesh on OK, and you see that the shape will improve. Yeah, but the number of finite elements goes by order to the third. So be careful not to have a real dense mesh, because your calculation will explode. But it looks really nice now. The meshing, etc. So what I will do now is add the pre-stressing load to the solid, and then we calculate, because we're interested what happens. And for this, we in all the trainings I say, okay, we can use Excel a lot, but in solid modeling you will notice that you will use parameters a lot. I think it's a really nice tool. So what I say, okay, there's FP. It's similar, this parameter, FP, and I have to define, okay, what is it? Is it the length? No, it is a force. Yeah, so force, and I can define the unit in kilonewtons. I start with minus 500, something. Yeah, and now what I want to do is apply this force to all these surfaces at the bottom, for instance. So I should know the diameter, dia, and it is a line. It is a length, excuse me. And I would like to work in millimeters. So this is I don't understand. I thought it was 20. So and then the area is something we also have, is area, and I can use here formula. There's something like P. It's in our system. P times, oh God, where is it? There it is. Times 0.25 times the dia squared. Top left, yes, sorry, this is German keyboard, I'm so sorry. Yeah, where is it? No, that one, that one. Well, hold on. What? Yes, sorry. If I enter and there's a mistake, it will be in red. So, but now you recognize this as it is okay, but it is not in square millimeters. But okay, this is it. That's an area, but the area is times 6. So what I have to do is maybe add something like 6. This is the whole area, and I will divide the full force over the 6. Yeah? So what I will say is something like pressure or stress. Press P is okay. And I say, okay, this is a stress. Stress, like that. And it is FP divided by the area. case sensitive, doesn't matter, so like that. And you see that it is, I will work in kilonewtons per square meter, it's like that. Okay, that is P, the value. It's calculated automatically, derived from this and this. Yeah. Okay, so turn this off. Now I will apply the load. Yeah, and I can do it in this way, that I simply say, okay, there is a load. Hold on, let me delete this. There is a new load case. Yeah, and the load case is pre-stressing. I don't want to have any. And this is a pre-stressing force, like that. Load description, okay. And there is a surface load, like that. I will define it in local z direction and say, okay, edit the formula. Sorry, I went too fast maybe. If you add parameters, you just have to click on this button and there's a set of parameters that are available to you. And use double click on that one, press apply, and there it is. Yeah. And so this surface load will be added to the surface, yeah, like that. So what I will do is something like that, and it is now applied, but I made a mistake in the parameters. So what I will do is say, okay, this is 500, like that. Huh? See, apply for the, yeah, that's okay. So this is the total load from the whole pre-stressing applied now to the individual surfaces. Yeah? And the surfaces are part of the solid. Okay, now it's easy. I already have the finite element mesh, so what I will do is start the calculation. Experienced users know they can show results here, and then it is automatically calculated. Yeah, you see that the 3D finite elements are also here in the equation, in the overview. And there's the result. Of course, there's at first there's some deformation, which is really small, like this. I will put it over here. And what I always do at the beginning is go here to the table and check, and this the results table, the summary. Yeah. So of course I check the deformations, but it seems not so illogical. But you see here that there is the sum of loads was 450. Yeah. And I entered 500. Yeah? And it is, I can already explain, it is because of your coarser mesh that I'm using here. If I look at really look at this meshing here, you see it. Maybe it's difficult to see, but I will try to show it. But here you see the meshing is like that. And if I improve it slightly, we see that the applied load and the reaction of the load is more. Now it's about the 10% difference. It's much better. So always take a look at this stuff. Huh? So in this case, I'm going to add because I've checked this, I will check the stresses later. I will add a mesh refinement here. Yeah. So what I will do is say, okay, new mesh refinement, not on the solid, but on the surface. Yeah. So say surface. Target length, let's start with 4 to have I hope this calculation handles it. And select cancel all. Select this one, that one. Maybe you can do it faster, but I like to see what is happening. So, and there's, I was checked it, the number 6, yes, okay, like that. Yeah. If I measure it again or calculate directly, it is you see that it is like this. Yeah. And you see it has increased to 487. It's not perfect yet, it's not 500 yet, but it's much better. Eh? So the meshing has influence of how we apply loads in this case. Eh? Be careful about it. So this is what I always check to have a relatively good mesh in this case and apply the load correctly. Okay, yeah, and you see here that if you look carefully, that the mesh is denser around these areas. Yeah. Okay, let's go to results back, and now we are interested. We can look at the solids, yeah, and then let's go look at this how do you say it, equivalent stress, the Vermeeses. There's nothing really going on, although I have applied 500 kilonewtons. There's something here, and people knowing from the previous seminar know that for stresses it's better to look at the distribution on constants like that. Yeah? But really, what we are interested in to look inside this, and there's something going on inside. And we see from the outside we see 0, but let's take a look. Yeah? So go to the clipping plane, and now we are able to look inside. Yeah? And we see stresses happening at the bottom of this connection, and it is almost 355 maybe. And so maybe if I apply a bigger load, there is plastic behavior already occurring. Eh? And that's why we use solids also, because this depth is important to take a look at. Yeah? When I change this slightly, say, okay, the steps are 10, I can go through it like that. See also the other solids, all the parts, and this is possible. Yeah? Okay, so this is, in a nutshell, a solid with cavities and stresses inside, and it is relatively deep. What I will do now is model the structure of an anchor and start from scratch again. Imagine in this consultancy case there was a concrete wall, yeah? And we had to apply the pre-stressing force on the concrete wall. And there was some boundaries, of course, the pressure that the concrete could carry, and yeah, so we had to take a look at that. And also the steel was S355 steel, so it shouldn't go really in plastic behavior. Yeah. So what we did was, there was a U-shaped profile and a tube, and I applied this load on the tube. Yeah. So I will do this 5, 6. Start again. Now I will go slightly faster, if I may. There is the grid again. So I start now from a beam, and this is U-shaped. I say, okay, new cross section, profile library. Yeah, there's a profile shaped. I used 400, I think, S355. So this part at this side there is a concrete wall. Yeah, and this is the spreader. Yeah. We took 1 meter, I think. 1 meter, spreading like that. So what I did is in this direction, and I say it is 1000. Yeah, it's like that. F8 is zoom. Okay. Escape. F8 zoom all. Now I go back to wire shape again. Here it is. The beam is here, and I will design now the member of the pipe. So in this case, it was like a tube pipe. It's something like, I will use something like this. 10, so yeah. New cross section, and it is something from here maybe to, I don't know, 750 or something like that. Yeah. So I'm looking at this. Yeah, where this part on the left is in the concrete cast in. Yeah. And also this is on top. Yeah. It was not straight, but always these anchors are on an angle of 30 degrees in this case. So what I will do is change this tube, rotate it. So what I will do is say, okay, select it first and rotate. Check this if nothing is okay on. Okay. Rotation is no copies. Rotation, I have to look at, I'm looking at Y direction, the Y axis. X goes to Y, Y to Z, Z to X. So I have to rotate it in negative direction, like this, minus 30. Yeah. Which point? Click on a point, and um, and it is in this case this point, yeah, like that, and it's rotated, yeah, and now it looks like this. This is more how it will look like. Now it is a simple set of members, not so two members in fact, with but I want to create now services from it. So what I did was, there's a tool, generate services from members, tools, generate services from members, settings, and here you can define how to create services from thin walled cross sections, so this U-shaped and tubes, and you can create automatically frontal plates, yeah, for connection from a surface to a member. You can use frontal plates, but in this case I don't have it, so I turn it off. I say okay, this is great, like that. Select them both, right mouse click, generated services from member, and now you see it looks different, but it the surface is created at the center line, yeah, of the tube, but for people wanted to have it really nice, we have always rendering like that, huh? And even better, I like when I work with surfaces, I use always this view, surface thickness, like that, huh? And so I check visually, is the thickness okay? Yeah. So I have now two surfaces like that, and I will have to apply the pre-stressing load, like the anchor, with the plugs on top of it. So to introduce, if I add here the pre-stressing load, it could maybe causes really high stresses in this case. Yeah? So what I will do is divide the two surfaces and create an intersection. So because if I look here, there's a surface inside. Huh? It's not there. So we'll do. Sorry. What I will do is this, like that. Come on. I use Control and the left to create, and then say right surface, create intersection. And hopefully you can see here, there's maybe a problem with the beamer, but there's now an intersection line here, huh? Like that. If I click on it and look at it in the Y direction, you see that this is an ovular shape, huh? Like that. It is the interaction line. You can convert it to a normal line. I won't do it today. Sometimes I use that, but it's a good tool. But still, it's blocked here. Huh? So what I go to data and say surface, and then I use this component tools. Huh? He created 4 different components: this one, this one, this one, and that one. Huh? So in this case, I'm not interested in this component. I don't want to remove it or something, destroy it, because the definition is by the surfaces. So I will only deactivate it. Like, and I always check. Yeah, I can look inside. Okay. This is a nice connection. I will later use this part to only support it, but that's later. What I will do now is create the similar solid, or set of solids, the anchor blocks on top of this pipe. Okay. So in this case, it is maybe nicer to have a different coordinate system. Huh? So what I do here is go here to this option, say coordinate system, create one that is local for the tube or something. Huh? So I say something like tube, click here. This is maybe a point. At the end there's a point, and then at the top there's the point. Yeah? And now you will see that there is a new set of arrows. For the global system, we have X, Y, Z. But for the user defined, we have U, V, W. Yeah? So, and later I can also copy in this local direction. So I will use this, check maybe if the grid, how the grid is, it is probably according to the new user coordinate system. So I lay it flat like that and move the zoom in like that. Yeah? So now this is my origin, yeah, for the new stuff according to my user-defined coordinate system. Maybe it's nice to add also, as an engineer, I like these lines a lot. So let's do this. It's also better for the picture later. So yeah, so we know where we are talking about. So this is roughly the dimension lines. You must know that the set of strands go through a hole of about 90. The tube is bigger, but the hole is about 90 diameter. So what I will do is at first is create a circle with a radius of 45. So what I will do is say, okay, new line. I like drawing with lines and later add the surfaces, but you can also directly create surfaces, doesn't matter. So I do this, 45, yeah. And I do it again, so I can, you can right mouse click, repeat new line, like that. And I could do it also instantly, but click it again, and now slightly outside. The tube is 180 something, so let's do something like 220. Radius is 110. Yeah. Yeah. Okay. So part is outside, and there's the future hole. You can use diameters also on radius. Maybe you know this already. If you are inside, it's like that. Or you want the radius, you go like that. Huh? Okay, for reference. So what I will do now is create a surface again. So surface, remember it's a null surface, like that. Click on the line. Yeah, that's what I like with drawing of lines. You can easily create surfaces. Okay, another one. Select boundary lines. Opening. I use this one. Yeah, there it is. Yeah, there's an opening. I can go look straight through it. So it's a null surface. Yeah, it's called 0 here, and you see it already in the coloring. That's why I like coloring. That you see, okay, this surface has a certain topics, and okay. So remember, this is a surface. I select now the surface, but I can copy it as a surface. But if I copy also the hole, it is like a ring, yeah, or how do you call it? Yeah, ring. So I have to copy the opening and then extrude it. I can extrude along the direction of user-defined coordinate system. I have something selected. Maybe you don't know this. I like this function very much. Alt-Enter, and you see here there you can select what you want to extrude, or maybe if I just right mouse click, it's like that. And hold on, where is the extrude? Yeah, extrude, like that. Yeah, and here it is. Yeah. Again, it was at 50. Let's use something like 30 for the ring. So you can do this. This is 30. Yeah, click, and there is now a nil. If I'm correct, there's a solid with a nil material, but I changed it easily to this, and now there's a solid like that. So here's a solid. If I select it, everything is highlighted. I will create now the, how you call it, the nut of the anchor, and it's on top of this solid. I can quickly use offsets and that sort of command, but also what I like here is that I can say, okay, there is now, if you look carefully, when we created the surface like that, RFEM left a help line. Yeah, it is a nil line, but it has still some information for use for me. So in this case, I will use this nil line and extend it to maybe a little bit. Or I'm still working in this local coordinate system. So if I do this, create this and say, okay, sorry, this line, member, nil, like that, and go in this direction, like that. Hold on, where's the coordinate system? There it is. Let's see. No, I will do it differently. What I do, I will first create a node. Maybe it's easier. So here's a node, and there's a node. So I use this function again, create new nodes. This one, that one. There's a new node in the middle, like that. So use this node and do it again. So draw this, like that. like that. So there's another line. I will later create also a result beam, and then this line is also very important for me. Okay, so there's the origin again. I'm working in this plane of this tube, like this. And I thought it was this. Now I'm going to move the origin to this point, create a new circle, for instance. Say okay, circle like that. Something like 70, is that, yeah, that's okay. Yeah, so it's outside. And I can also create other shapes. The nut is like a hexagon. Huh? So in this case, what I can do is say, okay, draw a line from this point, and if I snap here, you see the previews of the snap. If I change that and say okay, also for circles, object snap, partition points to 6, I get 1/6 of the circle, 2/6 of the circle. So in this case, I use this. Now it's difficult to see, but there's 5/6 like that. Yeah. So and I create now a new one that is over there. Oh, made a mistake, so undo. Yeah, do it again. Yeah, escape. Draw single lines, not a polygon. There's a preview again, like that, like that. And you see the shape is already happening. So I delete this one. I delete this circle, it was only help. Oh, sorry. Ctrl Z. They have similar notes, so let's leave it like that. Okay. I can create, if I have an existing service, I can create the services inside it. Maybe you noticed it already when you do other stuff, but if you click here, null service again, and click only on this line, it automatically recognizes this shape. I say okay. But now this question needs to be answered correctly. The new service lies directly upon another service. That is the automatic detection of the planar surface. Yeah? It doesn't work with curved, but only in plane. Do you want to integrate them? And what happens with integration is that he automatically creates an opening and places a new flat planar surface inside. Yeah? I say, okay, yes. So it's done now, like that. That was easy. And now you see this is the surface. And again, I can, if I select the opening, I can extrude it. So I will do this in this shape now. And now I'm going to copy it, but according to the coordinate system of the tube. And then I say the thick, and now I have to be, look here, there's a reference U is maybe 80. Yeah? And create automatically a solid. Yeah? We could create automatically surfaces. I did it in the first step, but you can also do it with solids and use the same template as the other one. So it's like that. It's like that. So there's the nut as a solid. Yeah, it looks really nice. Yeah, and now we want to let's close this stuff about dimension lines. Yeah, now we want to apply some loads to it, but first we have to think about how to support it. In this practical case, there was a surface support from the concrete. Yeah, so the concrete, I can select the web of the former U shape, double click, go to support, say available, and now I have to define the support conditions. And people who know me a lot longer know that I don't like infinite stiffness. So what I do is will type some flexible settings here, and I'd use 1E5 to the order of 10, that sort of stuff. But I will leave for now this nonlinearity of none. So it is pressure and tension. Yeah, I do. Yeah. Then I have to apply this. It's done here. I could use, and I will also apply it here. So this is now the component, but I can also supply also this support to a single component. Yeah? Okay, it's done here. So you can visually check it. It's over here. It's not there. This pipe part is over there. Yeah. So now it's supported, and in all directions, I think. Yes. So let's apply some load. So again, I use parameters, but hopefully I will do it slightly faster now, because the load introduction is important. If you apply like a nodal load on the solid, you get a lot of, the introduction is wrong. And in this case, in the nut, the inside there is like the wire. So the load is sort of applied on the inside of this nut completely. So this I will do. I will define by a nodal parameter is a nodal force, but by using parameters, I say okay, FP. Now we go faster. And they say, okay, this is a force. Let's start with minus 800. Yeah, check. There is diameter. There was something, I don't know. It was 90, I don't know. And the parameter, is this is a length. This is a length. The length is the parameter times the area times the diameter, like that. And then the area of the inside is the nut height. Nut. It's also length. It was, I think, 80. This is in meters. This is a disaster, of course. Yeah. So let's switch to millimeters. Like that. Like that. Okay. And then the area, the inside of the nut, is nut times peri. Like that. Yeah. Okay. And then you have some stress. So P stress is real stress again, and it is FP divided by area. Yes. Okay. That's the value I have to add at the end. Now let's take a look at this surface. Say okay, visibility, and if I click on it again, right mouse click, there is local access system. Yeah, of this surface. Sorry, I have to define it for the mesh. Let's generate the mesh. Like that. And if I display the mesh like what I did last time was here, display the mesh like that. You see this again, but you can also here go to display mesh and see after the, where is it? After the generation of the mesh, if you look correctly, the local mesh refinement of the finite elements. And you see here that the x direction is in this direction locally. So it means that if you apply the stress in the minus x direction, it is applied in the correct way. So this I will do. This is what I always do when I apply some load to a surface for solid modeling. So I say go to here to do surface load, like that. Say okay, it was good thing is what pre-stress is here, like that. And say okay, local x, apply the formula, go down pre-stress, like that, and add it to this surface, and there it is. Yeah, there is now the pre-stressing is like that. Yeah. Okay. Now we can. I already generated the mesh, but we can take a more careful look. Finite element mesh 50. There is something like a solid here of 30. Let's start with 30. The thickness is 30. And I use plausibility to check. There's also generate mesh. And if you get the result here of the kilograms, the mesh is okay, but you can always display it like that. Yeah, sorry, this one. So and you see here the mesh applied, like that, on both the surfaces as well as the solid. Yeah. Don't mistake this thick plate as a solid. It looks the same, but it isn't. It is a surface. But I use the rendering to draw the thickness. It's different than this one. This one. Yeah. Okay. Maybe you get a lot of. There's a lot of. I understand. There's a lot of access systems and information which you can turn on and off. Meshing is okay. Let's start the calculation. I think I applied the load. There was the boundary condition, so I can show the results. And it will probably take some time. No, it doesn't. That's great. Because I didn't have nonlinear supports, service support ready. That's a good thing for me. So let's first check deformation, which is highly exaggerated. You notice this. This will go here to this, and there's. But if you, in this case, go to 1, it looks like this. It's almost nothing. Yeah. Let's turn this off. Let's turn the load off, like that. Yeah. So there is the deformation. Let's take a look at the other stuff. We have something for surfaces. It's best to directly look at stresses, like this, and the stresses will look like this. And Walter will also explain later about plastic behavior, but you see the stress concentration is really high at this area. Yeah. And we can also take a look at the solid, like that. Solid. And it's a similar, so sigma x, go to the formesis, like that. And you see that there's now the solid is on top of a surface, and it's modeled like that. Yeah. Automatically, he detects there's a solid here, and there's the other one. And automatically, he transfers the deformation from the mesh, the Gauss points to each other. Yeah? Of course, I can look inside the clipping pane. Remember this. And now you can really look inside what is happening. Yeah? It looks a little bit disturbed, but it is the video card. Yeah? Like that. Or we can show other stuff. But first, let's take a look at what I did last time. And it was the sum of the loads. Yeah? So here, I think the pre-stressing force was 800. So in this case, I have to use. Do you have Excel, Walter? Yeah, you're probably. What I do is, if I have to check something, I say, okay, this is 684, 5, doesn't matter, and 395. Oh God, is this square root? Is it English? No. Huh? Wildsel? Ah, yeah, that's good. I learned something today. Wildsel. Like, yeah, but like that, sorry. Like that. I'm improving, see? So, this one. Boop, boop. Almost 800, 790. So, if I apply a better mesh here, you will get to 800. But this is always in the back of your mind. Did I apply the correct load? And you should take a look at this summary of loads. Okay, so this is important, I think, when I do this kind of stuff. Let's think about already about the documentation. That's what I would like to end it with. But first, I have some hand calculation, and I want to check it. And for this, we have the option of, we call it a result beam. There is a beam we have used the beam, but in fact there's a we can transform all the results back to a line and display the internal force. Yeah, internal force. This I will use here. If I zoom in, I will say, okay, this line, it was the help line, remember? I will change it to a result beam. Yeah, and the result beam, what it does is there's an integration area of all results from surfaces, solids or other members, integrated back to the internal forces on this beam. So in this case, I will use all. There's no member here, but like that. And I need to have some cross section. In this case, a tube, to define the result beam. Then I will calculate again. Now the calculation is done. You see here there's the tube is displayed. I will turn this off. Oh, gosh, what is? I'm destroying your laptop. Integration area, so like that. So now it's gone. But if I look at results, there is now the option of members. And if I go to transparent mode, for instance, the introduction of the normal force, and I turn off all the nice meshing and all the nice but not so important surface support, you see there's an introduction of, there is a normal force here. And you see along this line, it's about 800, yeah? And it is introduced in this area to 0. So it means that the complete pre-stressing was in the tube here. There was first in the solid, then in the tube. And then somehow it transfers. In effect, he goes to the boundary supports. That's what is happening. I think this is quite coarse. What I can do is say calculate. I think it should work. And increase the number of results for a result diagram. Like that. And say, OK, show results. Has to calculate again because he has to redefine. Yes, and it's slightly better, huh? Okay. It works for the normal force, of course, also for the shear force and bending moments, that sort of stuff, local stuff. So it's good for checking your hand calculation when you do solid modeling. Am I still using the correct model, and is my mesh okay? That sort of stuff. Yeah. So, by the way, I like this view. So what I will do and use this view when I create a printout report. Yeah? So this view seems to be okay. I go here to views and say, okay, this is my view for internal force. Yeah, like that, internal force. But I can create other views. I can say, okay, let's use, where was it? Some surfaces. For instance, this view is of the stresses. Simply say stresses. And maybe I want to take a look at the solid. Go to the results of the solid. It's also possible, solid, like that. But maybe I would like to go into detail, yeah, and maybe change something of the display. That I say I would like to have it more constant. Yeah, you see that this is quite coarse mesh for this nut. But maybe I would like to have ice. Oh, not this one. This one. Yeah. Some points. You can directly see there's a big stress inside a solid. I can also store this and say, okay, this is solid stress. Doesn't matter. And what I do now is to say, switch back. Yeah, there's internal force. There's something for the stresses. I can use this. And if I change it, it's automatically adapted. Yeah. Just for instance, if I it's just we take a camera shot, and with all the properties of the camera we store it, and with the selection it's all there. Yes. I forgot one thing. Now I want to change, for instance, one thing. I would like to have nonlinear or pressure-only surface support. I can directly go to the data, and it is already here. Surface support. You know, it's only one, and it's added to two surfaces, 6 and 7. So double-click here. There it is, and say nonlinearity. If the local gives negative contact stress, then you have to reduce the stiffness. Okay, like that. Do it again. Now it will run a nonlinear calculation, and we can also, when you open a model like this from a colleague, you have no clue what is inside. You can always check. Did he use something nonlinear? You go to calculation parameters, and here's the nonlinearities, and automatically you see that we use surface and elastic foundation supports nonlinear. It's always good to check. So this was adapted. So take a look at the views, the results, for instance, for the surface, and there in the surface there's now the contact stress. There is sigma z, like that. It's almost 0, and there is, if I do this, maybe you do this blue now. If you don't want the blue, just slide it like that, and it is like this. Maybe this picture is better for the printout report. So this is sometimes what I do also, and I say, okay, this is maybe better. So I select this stress and say, redefine current according to these settings. Maybe that is better. So, yeah. Oh, sorry. Oh, that's wrong. Yes. So, and now, so if I do this and this, it is better. Yeah. So we did nonlinear supports. In the end, with the consultancy, we did also plastic behavior, but for now, we will leave that to Walter's presentation. I would like to close this model and producing some pictures. Maybe you have to send something to a colleague. So maybe you would like to share this stress evaluation, and you would like to have it in 3D, for instance. You go to here to the printout, print graphic, 3D PDF. If you do this and say, that's great, speichern. He will store it as a 3D PDF. Anybody can open it who has a Adobe reader. It's automatically opened, and Adobe supports 3D models. And we create this for you, like that. And if I scroll down, you see there's a model, and there's also the ISO band which we have produced. This is, and now you can play with it. You can zoom in, zoom out, rotate, and take a look at all. This is the picture we have stored, and you can create it and send it. So 3D PDF is really nice to share something. The other thing is an actual printout report. So this case, I'll go to data and say, okay, printout report new. I will, for the numerical results, I will use template number 1. Okay. And then this is in English. All the stuff is there, but I can quickly reduce it by go to RFEM selection. I say, okay, I'm not so interested in all these results on cross sections, for instance, and that sort of stuff. I can turn it off like that. Then it's smaller. Maybe I should remove this one as well. Yeah. And so I'm going to move that one. So this one too, and this one too. Maybe the note table is gone. So because I use pictures. Yeah, and we'll change the language if I want to English, to French or Dutch. You know, W is wide, H double times is two pages at once. So there's my numerical data. Store this printout report. And what I will do now is create pictures based on the views. In the trainings, I will say, think about what do you want to report. If you want to have internal force, just use this picture from the, for instance, and there is, I can select here now, there is the member. I redefined it, now I know. So, service gone, something like this. Maybe use the direct Y, like this. Yeah, it's a good picture. And say, okay, like that. So I'm going to rate the picture of this one, print graphic, and now you understand why we have this option here. So go to printout, show printout not okay, mass print. Yeah, I'm going to create several sets of pictures. So what I will do here, say, okay, model, I will use the one that is provided when we have the start. Loads is okay. I can use simply isometric view, that's okay. Results, yes. I will use this picture, for instance, the current, and this one. And if I have multiple load cases, I can select which one. But in this case, I'm only interested in, there's a number of graphics in the member results, internal forces, so let's use VZ and N. So I always check this number of generated pictures is 3. That's okay, yeah. The second one, yeah. So I press OK. It's done now in the printout report. Control P again, or do this. Mass print again. I go now to stresses, for instance, this one. Yeah. Control P, the other view, mass print. Now I don't want to show any loads, but only results. Go to services, and there is already run. So that is the probably the phomesis. Yeah. No, it isn't. It is the contact stress. Yeah. So these two I would like to have from this view. Yeah. Okay. Not okay. I'm not going to the printout report on okay. And the final one is maybe the solid stress. Yeah? Something like this. Yeah? And I will use Ctrl P. Printout report current only. I don't want to mass print, but I would like to see the printout report on OK. So now automatically RFEM has stored the pictures at the correct locations if I did it correctly. If not, I can always make slight adjustments on the pictures. It's updating the pictures here, like this. There's a lot of data. Yes. Now you see why it is generating a lot. Here is the internal force picture from N, automatically according to my view. Here is from the shear force, here's from the bending moment, here's the view from the stress, and here's on the contact stress, and here's on the solids. Automatically generated based on the views, and it is adaptive, so if you change something, it is automatically done. There's also the load here, and there's maybe a mistake. Maybe I haven't done something wrong, so go to edit. And maybe I have to, I don't know what went wrong, but I'm going to fix it like that. And yeah, apply the load. I think it's back is okay. So, and then it will regenerate the picture. Yeah. Like that. And so could happen that something went wrong. Yeah. So that is I think it is almost time, huh? It's roughly 3 o'clock. In a nutshell, introduction of solid modeling. And I would like it was a consultancy job, and this is your end result. Huh? So the printout report is also important that it was there. So what we extruded something from a solid, from a surface into a solid, or we extruded surfaces from lines. We used user-defined coordinate systems. We used copy commandos. We looked a little bit at the application of loads. The meshing was there. We used tools like Result Beam, yeah, and we had 3D PDF for distribution of your model. And in the end, we had a printout report with all the hopefully the correct pictures and the data. Yeah. Are there any questions? Yeah, Peter. Yeah. 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 Okay. But you must know that there's a line inside the surface of the solid, and you should always take a look at how this stress is introduced there. But you can lose the plasticity module to smooth out results.
It was connected to the flange, this plate, this ring. Should you not make some contact property?
Yes, but maybe. You mean contact? Why? Where? Where, Peter?
Where the nut touch the
no, it's automatic. Yeah. If they share the same finite element nodes, the mesh generator does it. It is automatic. If you want to model something like a contact that you really have pressure only, for instance, it's different. That's what Walter will handle, all this advanced stuff. But remember that if you have this case, if you place a solid on top of a solid and there's nothing special, it will share the same nodes and the same meshing, and then it's okay. Yeah? Yeah? So, a lot of new nice stuff at the back. So about 20 minutes break, 15? 15 minutes. 50 minutes. Thank you for your time.